Hello everybody, my name is Uma. So today I'm going to talk about Apache Ozone, how that layout provides us efficient data storage, and how the applications can leverage Apache Ozone for your scalable deployments. I am working as senior engineering manager at Cloudera. Let me straight away jump on to the agenda for today. Uh, Today's agenda, I'm going to talk about what is ozone and the building blocks of ozone. Then I would go over the Apache Ozone architecture itself, how the redesigned architecture actually making it open for the exabyte scale capacity. And I would also take you through the IO flows, ozone IO flows, how well efficiently the data would laid out there. And I would also talk about the Apache Ozone user APIs, uh, so that how well that user APIs are closely integrated with many of the big data workloads today. Uh, and then I would go over the key benefits of Ozone. Then I would also talk on the community Apache Ozone community status. Then we would look at the roadmap, and I'll end with that. Uh, Let me go to my next the first topic. It's like what is Apache Ozone, right? Which is designed for actually fixing the some of the popular storage, which is HDFS, right? The shortcomings of HDFS and its limitations. HDFS is one of the successful storage project in a big data world. However, it's reached its limitations. Like after a couple of hundred millions of files, then it starts really seeing a lot of problems with single name node, memory pressure, and bigger block reports, several of issues when you look at the large deployments. They had to, the really engineering teams have to struggle to tune a lot of things to make it up and running, right? So this is the Apache Ozone designed mainly to keep that kind of scaling problems in mind, and it can support billions of objects with this Apache Ozone design. And as well as a single cluster can easily scale up to exabytes of data, and we use raft protocol for achieving the high availability of the master processes. We don't need to depend on any other zookeeper kind of distributed locking dependencies here. And we made this design made it like strongly consistent from the inception itself. And then the project released a GA release in 2020 back, and from since then we added a lot of features like ACLs and encryption and high availability, the replication. A lot of that got included in the initial GA. And it's fully integrated with a lot of popular projects like Impala, Hive, Spark, and then Iceberg, etc. And if you look at our community, it's like a really fast growing community. The lot of active contributors from Cloudera, G Research, Tencent, and DT, Shopee, and QA, and whatnot. There are many other contributors are coming in our Slack channel. It's more than closely 300 folks around in the Slack channels. And some of the users are already deployed this Ozone at the scale, and they're running. So, and next, what are the building blocks of Ozone? If you look closely in the Ozone, I was talking more about the design, right? So if you look closely to the building blocks of Apache Ozone, it's basically the key bottleneck in the other storage system like HDFS has. Namespace management is the biggest challenge because it's a single place which maintains all the blocks and namespace in the same process, which really gives a hard time to handle that scale, because of the GC pressures and many other single lock on a whole namespace, right? So here, in this Ozone we have like a namespace is separated, which maintains by Ozone Manager, And the storage container manager, which specifically tracks the containers. The containers here is logically grouped several of blocks, so no individual block reports has been sent from the storage nodes. The storage nodes, you call it as a data nodes. The data nodes store the actual physical blocks, and they group together as a logical containers, and they report to the storage container manager. These two processes mainly to track the metadata space of the system. Um, and we use underneath the rocksdb to keep the metadata, so that we don't keep everything in the memory. And this design, we kept this as an object storage in mind, so that there are a lot of modern the new trends, like going with the S3 kind of protocol, so that we kept that as in mind and designed to have a object storage as a main goal here. So that brings us like having a bucket and volume separation in our architecture, so that way the locking can be like segregated within the bucket level and volume level. And there are several improvements going on further to improve that, so that we don't need to have a single lock in the whole system. So this block management independently make us like scale the billions of files. We have tested billion levels of files in our some of our test clusters. Let's look into the ozone architecture in detail, right? So if you look at ozone architecture, and I just discussed about this separated layers, where the ozone manager only takes care of the key space, which is a file versus where the containers are mapping to. And the container locations are never tracked by ozone manager. The storage container manager is here actually block space management, which will track about the where exactly that containers have been located in the storage nodes. That way that we have other process like for the easy maintainability, like ozone recon, which actually provides all the statistics details of the cluster, so that users can actually make benefit out of it to get insight from the cluster what is happening. And the clients will talk to the ozone manager, and ozone manager underneath we have a raft which maintains the consistency to provide the high availability. The multiple nodes of the ozone manager access provides the high availability, even if one node goes down, which is still highly available. So then the client gets the metadata details to the client, and then it knows, based on that it knows where its block is located, because it piggybacks to the storage container manager to get the actual locations, and it sends to the client. So if you look at like the flows, like I said, we use a raft in each of these processes for getting the consensus, and then it push back actual metadata to the rocksdb underneath, so that we don't need to keep everything in the memory. It keeps rocksdb has its own caching techniques to keep the hot piece of data into the memory, and it has its own caching techniques. We use that. We have our own top layer of the caching as well, so that way we don't need to really bother about on the external IO here. So if you look at the each block space level, the how the blocks has been replicated, we still use a raft in the block level also. So when the data is sent to the one of the leader within the data nodes forward that data to the followers. So if you look at the data node structure a little closer, so this is how the containers, right? So the containers will have the bunch of blocks, but that container is logically grouped as a single entity, and that would be reported to the SEM. So the locations of these containers would be in a different data nodes underneath, and that locations would be tracked by the SEM. and Ozone Manager will keep ping to SCM to get the actual locations where they're actually located on the fly based on the request from the clients. So we can look closely into the operational view. Let's say if you look at the metadata, how it's laid out, and then how it's got queried from the different nodes here. Like let's say client wants to read store a file, like let's say key one or key two or key three, key four here, bunch of examples I provided. So they're let's say they want to place the block B1, B2, and map to the containers. It's like a C1 here. That the containers have been allocated in SCM, but however, it's just a metadata. The containers and where it wants to allocate, it's like a data node 1, data node 5, and data node 6, let's say, in this example, right? So which provides the mapping where it wants to store the data. So the data node 1 and 5 and 6, if you go here, data node 1 and 5 and 6, they have the container C1, 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 right? So that can keep the physical blocks associated to that container. So each key can map to a specific container. One container can be mapped to multiple files. Multiple files can still put their blocks into the containers, because container with space, we keep it as like 5 gig in size, so that data nodes need not report each block level health to the storage container manager. Data node themselves will take care of the block space within the nodes, and it tells whether the container is healthy or not. So our replication unit is at the container level, not at the block level here. All right. So that way the client gets the mapping of the corresponding blocks, and it connects directly to that blocks and reads back to the client. So here in this case, the single process is not maintaining whole metadata. And the reporting structure also changed from the data node. They don't need to report each block level to the client. That's how the scaling is possible here, so that the maintenance of the metadata is much lower in the single process. So this shows a little bit of flow connectivity, how the containers are mapped and blocks are mapped underneath the data nodes, and the client can interpret to read the corresponding blocks. Okay. Let me go on to the this is just what I explained. So here in this case, I just showed the path. Like we have abstractions due to the like 30 minutes time here, I couldn't explain really like what is volume, what is bucket here. We have a notion of like a volume and bucket. The volume is basically a higher level of abstraction, so that you can have a multi-tenant kind of layouts you can design. The bucket is like a very similar to the S3 Amazon S3 bucket kind of thing. You can create a bucket, and underneath you can put a bunch of keys inside that. So for the namespace perspective, which is like we have two different layouts. One is a directory based layout, which to comply with the similar file system use cases, and we have a flat key value kind of layout, which is very similar to the object store in Notion. So the next topic is about the user APIs. The user APIs, we have two key API sections here. One is the file system, and other side of the user APIs are like Amazon S3, which is similar to any of the S3 applications can just access this Ozone system. So yeah, so basically the file system Hadoop itself has a file system abstraction. So there are a lot of file systems got implemented that, like Amazon S3 file system, ADLS, and similar to that, Ozone is one of the file system. Based on the scheme OFS, the system will redirect to this Ozone file system. So this is how the many applications use Hadoop file system interface today. So that's how this integration with Ozone file system is like a seamless transition. So if you look at the S3, S3 is like a HTTP based, and we have S3 gateways which will interpret your requests and transfer to the Ozone. You can have as many as S3 gateways in the system. You can just put a front load balancer to that. This is pretty much like a stateless, which will just redirect to the corresponding key or object in the Ozone system. So this gave us a dense storage advantage, whereas in HDFS kind of systems, since it has to report all, it has to track all the blocks. So the if each node has its large capacity, then it has to report a lot of blocks to the container managers or namespace managers, right? So here in this case, we only track at the container, so it don't need to send the each block report. So the reporting the payload is like much less here, because it just send the containers report. So that way it opens up us to add more storage so that it can store more blocks in the store in the data nodes, each individual data nodes. So we tested up to 400 terabytes of capacity level. So this is like one of the key differentiator compared to any other storage today. So let me quickly look into the IO flows. As I said, like we have two IO flows. One is replicated and other one is eraser coded. I'll quickly go through the replicated flow here. In the replicated flow, we use Raft today, so that the client will send the data to the primary leader, one of the leader. Each data nodes like peaks as based on the replication, like for three replication, they themselves form as a raft group, and the clients will pick one of the pipeline and sends the data to that raft group leader. So the leader will forward that data to the followers. So that is about the write flow. Then the client commits the lengths until where it committed into the block to the Ozone manager, and the Ozone manager keeps track of the length of the block. The semantics of Ozone is like is kind of object storage based semantics. Like the put is basically it will only be visible once the put is completely done to the user. So that way the client actually can inform the accurate lengths to the servers instead of learning from the data nodes until where they wrote. So the reads are straightforward. So since it has a mapping and the backend, it talks to the container manager about the locations, and we have also caching here. So the clients can directly talk to the nodes in order based on the locality. If they are closer to the client, then it just talks to the DN1. In this example, let's say if you assume data node 1 is closer, then it talks to the data node 1 and read the corresponding block. Okay, next we have another IO layout. In this IO layout, which we use eraser coding underneath, right? This is the quick comparison between the three-way and eraser coding, right? In a three-way, you need to maintain the three duplicated copies of a data in the cluster. It's a costly, right? You need to have a large hardware to handle this. What if you can like save the 50% of storage space to use more data, right? So this eraser coding is a popular technique, many of you know, like which can without any duplicate of data, but it generates some kind of additional parity, which is much less compared to the duplication of the data. In this example, if you see the block ABC, if you want to store, you need to store around 9 copies to provide the durability, right? Two nodes, any of two nodes can go down here. You will have still one more copy. In eraser coding, let's say for the same ABC blocks, it only generates parity of additional two. Then you can still lose any of two nodes here. Let's say in this example, the B and P1 lost. The eraser coding can actually decode the B and P1 back, and it can serve users back, right? We have different schemes. In this example, I gave you 3-2, right? 3 data and 2 parity. We support 3-2, 6-3, and 10-4 schemas here. So that 10 4 means 10 data blocks. For every 10 data blocks, you just store four, you would just generate four parity blocks and store it. So that means that for 10 blocks, in three-way replicated, you need to store in like 30, right? 10 into 3, 30. But here in just you will store in for 14 replicas should be sufficient. That's how your storage savings should be up to or greater than 50% efficient storage layout. So in Ozone, we support this layout. So we chosen to go with the striping model, which is not each individual block will not have a contiguous data here. The data, let's say here, like 1 MB of each chunk is split into smaller units and send it to the data nodes. We call it as a block group here. So each contain, let's say here the C1 is placed into the 5 nodes, because in this example I took 3 to example. So 3 data pieces and 2 parity pieces, right? In the same container, the block one, in the block one will be created in all of these 5 group nodes. In that, first 3 will have a data and last 2 will have a parity. uh, the 1 MB chunk unit level, we transfer to first 3 nodes and generate a parity and send it to the N4 and N5. And again, we come back and the fourth MB will be sent to the N1. And that way, in the round robin fashion, we split this data. The reason is, if you have a small data, for smaller data, we need to be able to generate the still parity, right? We cannot wait for until 256 or 128 MB of size to be filled from one node and generate a parity. So every smaller unit level, we want to generate a parity so that you will have the durability as soon as possible, right? So that's why we keep it as a optimal size of like 1 MB. After 1 MB into the data pieces, it generates a parity. When you have very small chunk, it uses the padding data and generates still parity. But padding data, we don't store it. Based on the length, we figured out whether there is a padding or not. So we don't occupy any of the additional space here. So these are the multiple examples of based on the file sizes. Here, just 1 MB, 2 MBs in size. We use the third 1 MB as padding and still generate eraser coding parity data here. So in this case, it's the best example. You have 3 replicas and you generated a parity. So of 2, right? So this is the write flow. And if you come to the read, we don't read in very happy flow. We don't read from the parity. You could have a question that why you are not reading in N4 and N5. N4 and N5 will be still used by different containers. So the distribution is still achieved. We don't leave dedicated nodes only for parity. The N4 and N5 will still serve other containers, which can be data blocks there. So here, for read, if you look, it reads from the block 1, block 2, and block 3, and again goes to the block again to the same first node and second node and third node, right? In the round robin fashion, in the same way, it reads from the data pieces and stitch it back at the client and serve to the user transparently. Even if any of the block lost here, it's still that time we use the parity block to reconstruct transparently and send it to the client. So user will not see any of these failures directly. So it will be transparently reconstructed and send it back. We have also offline reconstruction, so that to avoid this any of the node loss issues. So it itself will reconstruct. So in summary, the key benefits of Apache Ozone is like it has a flexible file system interfaces, file system and S3, and resilient for hardware failures because it itself can reconstruct and recover the blocks back. And efficient storage layout, as I said, like EC and all. So seamless integration with many of the big data applications like Spark and Iceberg and etc. And the dense storage, as I explained, and the beyond scaling capacity because of the split of the namespace, we get open up to able to go beyond its limits. And the community is very healthy and one of the most active project, if you see, in Apache Foundation. And the features set is also like growing, and we have the features like the snapshots, multi-tenancy, etc. Supports, and we are keep working on the feature roadmap. And if you in a quick summary, if you look at like our current project chair is Samichin, and we have 36 PMC members and 74 committers, and they're located in all over. And there are many companies involved. The committers are all around from a different, diverse set of companies, and there are 200 plus contributors and 6,500 plus commits in total. And the project, the lot of activities going on, like 9,500 plus jiras open under the open source HDDS project, if you look. And the jiras, like last, if you just look at the last 2 years, we have 200 3,600 plus jiras open, and closely 3,000 jiras got resolved. That pretty healthy activities going on. And if you look at our roadmap, since the API semantics, like it's not visible until commit, right? But H-based kind of projects need to read even before closing of the file or key, right? So for that kind of support is being worked on. So that's in our roadmap, and we are actively working on, like, and also we provide a lot of improvements for the recon for the users, and the data storage tiering, CSI support, rolling upgrades, deduplication, solar support, and many more is coming in as part of our community activity. And if you are interested, we are very inclusive community, and we are happy to get you onboarded, and we'll be very happy to work with you. If you are interested, please reach out to us through any of these medias. And we have a community uh, contribution guide through these wiki pages.